Hey you guys, welcome back. On today's notes, we're going to be talking about infinite geometric series. And we're also going to be talking about what it means for a series to be a convergent series or a divergent series. In a convergent series, we can find a sum, and in a divergent series, the sum is infinity, so there's nothing for you to find. That's the gist of it. So in Google Classroom, you can print these notes out, and I'm going to go ahead and make sure on the top of these notes that I'm writing my name. And this is Unit H, Lesson 6, and the date, which is April 17th. And my period number. Okay, that way I can grade these easily. Please and thank you. Okay, so let's dive right in. So let's look at an infinite geometric series. There's actually two examples given here, and the first thing I want to point out, if you look at what I'm pointing at here, is that this ellipsis symbol, this dot 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 at the end of the sequence, tells me that this is infinite because it goes on and on and on. Okay, it's not a finite sequence or series where it stops at a certain number. It just goes on forever. The difference here is going to be in the r value, and we'll explain why. So in the first example here, we have some of the terms, the first four terms, and they're asking us to find in the first column, in the first row, they want us to find the sum up to the first term, the sum to the second term, sum to the third, and so on and so forth. So let's fill that in. So the first one is simple because it's just going to be whatever the sum of the first term is, which is itself. So that's going to be 0.5, because 1/2 is 0.5. The sum up to the second term means we're going to add the first two terms together. So if I take 1/2 and I add that to 1/4, then I'm going to get 0.75. So let's fill that in our table. And now I have to do it again up to the third term, so I can just take where I left off and add 1/8, 1/8, and I get 0.875. And now let's do the fourth one. So add 1/16, and we get 0.9375. And we also need to find up to the fifth term. They didn't give that to us, but we can pretty much deduce what it is. The denominator is doubling each time, so the next term is going to be 1/32. So add 1/32 to that, and the sum up to the fifth term is 0.96875. It looks like there's actually space down here for one more term, which would be the sixth term. The sum up to the sixth term. So if you want to write that in, I'm going to write that in too. So the sum up to the sixth term, if you double that denominator again, would be adding 1/64, and you get 0.984375. Okay, so what I want you to notice about the pattern here is as you continue to add the terms that are in this series, what number are you getting really close to for your summation, right? And it looks like we're getting really close to 1. So the sum of this infinite series is going to be 1. If we applied the formula and did all of that mumbo jumbo, we would get 1 as our answer. But I'm just pointing out the pattern here is that it's getting closer and closer to 1. It's going to take longer and longer to get there, because if you think about it, as you continue moving through the sequence, the number that you are adding to the sum you already have is actually getting smaller and smaller. 1/64 is much smaller than 1/32. 1/128, that's the next term in the series, is going to be way smaller of a number, way smaller of a decimal that you're adding to 1/64, the sum that you've gotten so far. So it's as you get closer and closer, it's going to take you more and more terms to get closer to that value of 1 because they're getting smaller and smaller. So remember what we said in our last lesson about a geometric series and sequence is that when the sequence is getting smaller and smaller, that means the r value must be a fraction, or that means it's less than 1. So in this case, the r value, we can actually tell what the r value is, because what do you multiply a half to get a fourth? It's by a half. What do you multiply a fourth to get an 8? It's a half, and so on and so on. Okay, so in this case, our r value is a fraction. Let's look at another example. And in this other example, we're going from a half up to 1 to 2 to 4 to 8. It's getting larger and larger. The numbers in this sequence are getting bigger. So the sum up to the first term is 0.5, because it's just the first term. The sum up to the second term is 1 plus a half, which is 1.5. The sum up to the third term would be 2 plus 1.5, which is 3.5. And then you're going to add 4 to that, 7.5. And then you're going to add 8 to that, which is 15.5. And then the next term that's in this series is going to be 16. So you're going to add 16 and 15.5. That's 31.5. And what I want you to notice about this pattern is that the numbers, the sum, is getting larger and larger and larger. It's not approaching a particular value. It's not going to get closer and closer and closer to, let's say, 32. It's going to be basically double of 32 at this point if you continue adding on to that. So in this example, we have an r value that looks to be multiplying by 2. So the r is 2, because every time you go through this, you're multiplying by 2. And we're not approaching a certain value. So the difference between these two examples is that when the r value is a fraction, your numbers are getting smaller, but the sum of those numbers is getting closer to a particular value. That is called a convergent series, okay? And then the other type that you could have is a divergent series. The r value is greater than 1, and so your numbers in your sequence are getting larger and larger and larger, but when you add them together, they're not getting closer and closer to being one particular number. It's just going to be a bigger number as you keep going. So that's the difference. And in general, what we can say is that if the r value is, well, actually it would be the absolute value of r. If the r value, so it doesn't matter if it's positive or negative, but the absolute value, if that absolute value of r, if that's less than 1, or it's a fraction is what that's really saying, then the series is going to be convergent. And if that absolute value of r is greater than 1, so it's 2, it's 4, it's 100, it's something larger, not a fraction, then the series is divergent. Okay, so we're going to apply this in practice. I'm going to flip this over, and we're going to do some examples. The first thing to know before we can do the examples is that in a convergent series, you can find that sum. You can find what number it is that sum is going to keep getting closer and closer and closer to. In a divergent series, you can't, because the sum of that series is just, it's infinity. The number is getting larger and larger, and it doesn't approach a certain point. It doesn't stop. So we can only find a sum if it's convergent. And the formula that you use to find that is the sum for a convergent infinite geometric series is the first term, and that's going to be times a value, which is 1 over 1 minus r. So if it's convergent, we're going to use this formula. If it's divergent, then we're just going to put no, we can't find it. Okay, so we'll do our first example here, which is number 9. Number 9, we need to figure out what is r. So what is happening here? The r value can be found pretty easily by starting at the right side and then dividing as you go closer back to the first term. So if you do 1 over 64 divided by 1 over 16, remember I'm going from the right side dividing to the left to find the value of r. So when I do that division, I get 0.25 or a quarter, whatever you want to write. I'm going to put 0.25. And then when you define the same thing again from 1/16 to 1/4, so 1 over 16 divided by 1 over 4, and that's 0.25. And then the same thing again, 1 over 4 divided by 1. Well, anything divided by 1 is itself, so 0.25. So our R value is 0.25. So since this value, this R value, is less than 1, yes, this is convergent. Yes. And so if it's convergent, that means we can find the sum. And so let's go ahead and find the sum. The sum of this series is going to be the first term, which is 1. And that's going to be multiplied by 1 over 1 minus r. So 1 minus 0.25. Well, 1 minus 0.25 is 0.75. So if we use our calculator and we do 1 divided by 0.75, and you multiply that by 1, the sum of this series is going to be 1.3 repeating. 1.33333, or 1 1/3. And so that's all you're looking for here. Remember, these fractions in this series are getting smaller and smaller and smaller. So the pieces that you're adding onto your sum as you continue through that series are smaller and smaller and smaller. So it makes sense that eventually you're just going to get closer and closer to this one value. You're not going to have, where it just keeps getting into a larger and larger number. Okay, so let's check out number 10. We need to find the R value here. So let's start at the right, and we'll do 128 over 3. Whoops, put that correctly in the calculator. And we divide by the term before it, which is, in parentheses, 32 over 3. And we get 4. And let's do the same thing again. And actually, because the denominator is not changing here, the numerator is changing. I really don't even need my calculator. I can just look at the numerators and find out what's happening. And 32 divided by 8 is going to give me 4 again. And 8 divided by 2 is going to give me 4 again. So I know that the common ratio here is 4. So remember, when the R value is larger than 1, if it's not a fraction, then that means that, number 1, our numbers in our series are just going to keep getting bigger and bigger and bigger. And that means our sum is actually going to keep getting bigger and bigger and bigger. We're not approaching one particular value. It's just going to be a larger number every time we add another term to it. So this is a divergent series. So we're just going to write divergent, and that's all we have to do for those. So remember, if it is convergent, if the R value is a fraction and it's convergent, then you use the formula to find the sum. If the R value is greater than 1, it's a divergent series, and the sum is going to be infinity, so you can't find the sum. Okay. So for your practice, we're going to go ahead and leave you 11, 12, 13, 14, 15, and 16. And before I leave you, I do want to talk a little bit about the ones at the bottom here that have sigma notation. So something that's different about these that you have not seen before is that the value on top of the sigma on all of these problems is an infinity symbol. So that is your clue that this is an infinite geometric series. Okay. Next to it, you have the rule that describes that geometric series. And so you can tell immediately what the R values are for these by looking at what's being raised to the power. So if we look at 13, what's being raised to the power is 1/4, and 1/4 is less than 1. And so that means this is convergent. So we can find the sum here, okay? And remember in the rule, for a geometric sequence, you have A1 times the value of R to the power of n minus 1. So in all of these problems, you also have a sub 1. You have the first term of the series already. So that's all there is to it here, guys. You just need to remember what's A1 and what's R, and you need to plug it into your formula, and that's all you need to find the sum if it is a convergent series. If it's divergent, then you can't find anything, so you're just going to have to You're just going to have to say no to that one, okay? All right, so that's where I'm going to leave you with this. Remember, your notes is part of your grade for this, and also completing the practice problems, which is 11 through 16, is the other part of your grade. If there's anything from this lesson that's you need clarification on or need help with, please feel free to pop into my office hours. Those are on Tuesdays and Thursdays from 10:30 to 1:30. And I'm also available basically any other day of the week that you need assistance. Just send me a message on Google Classroom or email me or remind, and we'll go ahead and link up and help you out. Okay, guys, thank you so much for watching, and I will see you next time.